Welcome back to the wonderful world of astronomy. This is the beginning of Chapter 4, and in this next unit, which is Chapters 4 and 5, you're going to be getting your introduction to physics and chemistry. Now, this is all the foundational science that is necessary for having a good understanding of astronomy. Before we start looking at the things out there in space in depth, such as planets and galaxies and stars, we want to make sure that we have an understanding of all the concepts we're going to talk about. Chapter 4 is called Making Sense of the Universe, Understanding Motion, Energy, and Gravity. The picture you're looking at is of two galaxies, and so they are comparable. They're like the Milky Way galaxy. They are both spiral galaxies. Now, interestingly, they are gravitationally bound to each other, and as they've come together very slowly over the course of a few 100 million years, they actually start to warp and change each other's shape gravitationally. They are colliding galaxies. If you look at the yellow centers, such as this one here and that one, and just all the brightness of it, what you're looking at is billions upon billions of stars. Now, for the most part, you can't pick out the individual dots that make up all those billions of stars, but collectively they give off light, and they're giving off light of certain colors. You can see some yellow, maybe some orange, some blue, and white. And through the course of chapters 4 and 5, we're going to be looking at why these colors and why are these galaxies the shapes that they are. Well, if we're not going to be looking at answering those questions directly, we're at least going to lay down the foundation for that we can better understand that when we study galaxies. So let's get into it. Chapter 4, Part 1, Introduction to Motion. How do we describe motion? In science, we need precise definitions to describe motion. So I'll introduce some words to you, and those words have slightly different definitions to what we're used to using in everyday language, but we have to make sure that we're defining our words properly. It is important for our understanding of motion. Speed is the rate at which an object moves. Now, that isn't any different from the everyday word of the language, use of the word in our language. Speed, mathematically, as a quantity, is distance divided by time. So if something travels 20 miles in 1 hour, it was going at a speed of 20 miles per hour. Often in science, we don't use units like miles and hours. Often we use metric system miles, or metric system units rather. And so meters are the standard unit of distance, and time, the standard unit, is seconds. So often we'll be saying the speed in meters per second. So if something goes 10 meters in 1 second, it's going at a speed of 10 meters per second. The next word, velocity, is one that in everyday language is synonymous with speed, but it has a slightly different definition. Velocity is speed, but it's also direction. It's got the two components, speed and direction. So if I say that I was moving at 10 meters per second, I'm expressing a speed to you. But if I say I was moving at 10 meters per second due east, that's the velocity. So velocity includes speed and direction. Now, it seems like a nitpicky nuance, but as I said before, it will be important in our understanding of concepts of motion that you understand that velocity means speed and direction. And that brings us to the next concept of acceleration. Now, in everyday language, acceleration means speeding up. But sometimes we can refer to a negative acceleration, otherwise known as a deceleration. When your car decelerates, it means you're slowing down. Well, the precise definition of acceleration is it's a change in velocity. As a mathematical quantity, it's how we measure the rate of change in velocity. But I want you to understand this. It is change in velocity. So anytime velocity changes, there's an acceleration. And now this brings us back to our definition of velocity. Remember, velocity is speed and direction. So anytime you have any change in any of those components, you have an acceleration. The units of acceleration are speed per time. And so remember, speed is meters per second. And then we're dividing by time, so it's meters per second, but we simplify that and say it's meters per second squared, because it's per second per second. Now let's look at these three examples with the car. These are all examples of accelerating. This car at the top, it was going at 30 kilometers per hour. It sped up, and now it's going 60 kilometers per hour. And so because it changed in speed, which is a component of velocity, it was an acceleration. The car in the middle was going 60 kilometers per hour, finished going 60 kilometers per hour, never sped up or slowed down, it's just driving in a circle, but it's changing direction. And because direction is a component of velocity and direction changed, it's an acceleration. Now, if you go up and you look at how I describe the unit, speed per time, speed per time, and you think, well, how does that relate to this, because the speed never changed? It gets more complicated than that in ways that we won't get into in this class. We won't be measuring the acceleration when a direction change is involved. At the bottom, we've got a car that was going 60 kilometers per hour. Now it's going 0. It came to a stop. Well, since it slowed down, its speed decreased, and therefore its velocity decreased. So it was an acceleration. So to summarize this slide, an acceleration happens anytime there's a change in speed or a change in direction. Now, near the surface of the Earth, everything accelerates downward at the same rate. As long as there's no friction or air resistance, you let go a helium balloon and it goes up. Well, that's totally different. There's a buoyancy force where the air is actually pushing it up because it's lighter than air. But if we just take two rocks, a brick, something with no air resistance, we just drop it. All falling objects accelerate at the same rate, assuming there's no friction or air resistance. On Earth, that rate, we give it the lowercase letter g in our mathematical equations, and it's about 10 meters per second squared. Really, it's about 9.80, but in this class, we'll just call it about 10 meters per second squared. Now, what that means is, if you drop something and it's got enough distance to fall, like in this picture, if we drop this object and we start, right as it drops, we start a stopwatch. So when time equals 0, its speed equals 0. And then it starts to fall. 1 second later, it's moving at 10 meters per second. That's the idea of acceleration of 10 meters per second per second. Every second that goes by, it'll gain another 10 meters per second. Assuming it has more time to fall, a great distance to fall, after 2 seconds, it'll gain another 10 meters per second. So it's up at 20. After 3 seconds, it'll be going at 30 meters per second. And again, every second that it falls, it gains another 10 meters per second. Galileo was thinking about this in the early 1600s, and people in his day just assumed that heavy things fall faster than lighter things. And Galileo showed that actually it doesn't matter how heavy or light something is, as long as there's no air resistance, they will all fall at the same rate. The legend says that Galileo went to the top of the Leaning Tower of Pisa and dropped a heavy object and a light object. As far as I can tell, I don't think he actually went up to the Leaning Tower of Pisa, but he probably did this off of some tower. Certainly he mathematically proved it. So you can do this experiment at home. You can do this experiment at home. I did this off my balcony at my home with a heavy water bottle on the left and a ball on the right, but unfortunately I can't get that video to play right now, so you'll just have to take my word for it. They both fall at the same speed. You can do this at home though. Galileo showed that g is the same for all falling objects. Remember g, the acceleration due to gravity, as long as there is no air resistance. And so this is a paratrooper who's jumped out of an airplane, and the purpose of a parachute is to give that air resistance. So he or she is no longer falling at 10 meters per second squared, but is being gradually brought down because of the the good air resistance from the parachute. The next concepts I want to talk about are momentum and force. Momentum is a quantity of motion, and it's an object's mass times its velocity. Now, if we take into account the direction component, what that means is that whatever direction something is moving, that's the direction the momentum is pointing. If something is moving to the east, we say its momentum is towards the east. The numerical part of this is mass times velocity. So the more mass something has, the more momentum, the faster it's going, the more momentum it has. And you can think about a bus going down the street very fast. Now, a bus is very massive. A bus, if it's going very fast, it has a lot of momentum. And it can do a lot of damage if it hits something. If it collides into something, it'll impart its momentum to that other thing. Now, contrast that with a little tiny a bicycle. It could be going the same speed as the bus, but it's not very massive. And certainly it's got momentum, and it can do some damage if it hits something, but not nearly as much damage as the bus would do. So momentum is a quantity of motion that is mass times velocity. Now, momentum will change if a force is applied to the object. And I say a net force. Net is the word we use to mean total force. So if we're doing a tug of war, let's say I pull on a rope with 100 pounds of force one way, you're pulling 100 pounds of force the other way, it's not going anywhere because our 100 pounds are canceling each other out. We're pulling in opposite directions. So in that case, the net force is 0. But now imagine that we are pushing something together. Maybe we're pushing a stalled car down the road, and I'm applying 100 pounds of force and you're applying 100 pounds of force. We're both pushing that car. Then our 100 pounds are adding together to 200 pounds. That's the net force. So net force, you can just substitute the word total force. And it's not just simply a matter of adding the 100 pounds plus 100 pounds, because there's a direction component involved. As you think about my first example, if we're pulling in opposite directions, then they cancel each other out. But a net force on an object will change its momentum. So let's go back to the example of the stalled car. If we are pushing on it, we're applying a net force. We will change the car's momentum. In that case, we will give it some speed, and we'll get it moving. And that generally means an acceleration, which is a change in velocity. There's a special kind of momentum called rotational momentum, otherwise known as angular momentum. If something is spinning or moving around in a circle, like a planet orbiting a star, we call that angular momentum. Now, let's think about, before we move on, for each of the following, is there a net force on the object described? And think yes or no. A net force, a total non-zero force. So a car coming to a stop. And I want you to think of it this way. If that car accelerated, and even though it's coming to a stop, remember what acceleration is, a change in velocity. If it had a change in velocity, that means it has a change in momentum. And remember what causes a change in momentum? A net force. So a car coming to a stop, yes, it has a net force. What about number 2, a bus speeding up? Well, it's changing velocity, and that means it's changing momentum, and there's a net force required to do that, so yes. An elevator moving at a constant speed. And the key phrase there is constant speed. Constant speed means it's not accelerating. It's going up at the steady speed and it's going down at a steady speed. It has momentum, and that's not changing. And so there's no net force on it. So number 3 is no. Number 4, a bicycle going around a curve. Well, just like in a previous slide, the car going around a curve, it is changing its velocity. It's changing its direction. Therefore, it's changing its momentum. And yes, it does have a net force. And finally, a moon orbiting Jupiter. And I see the moon orbiting Jupiter as very similar circumstance to the bicycle going around a curve. We have something that is moving around, it's changing direction because it's going in this elliptical orbit around Jupiter. Therefore, it's accelerating. Therefore, it has a change in momentum and therefore a net force. So there's all the answers. There's a special concept in physics called conservation. And as we learn in these two chapters, we're going to see some various applications of conservation. Conservation means that the quantity stays the same. And this is conservation of angular momentum. Notice as we're watching this planet go around a star, and we could also pretend it's a moon going around a planet, notice as it gets closer, it speeds up. And as it gets farther, it slows down. Well, angular momentum, which I defined earlier as the momentum of something that's either going around in an ellipse or a circle, or something that's spinning on its axis, is mass times radius times speed. And radius you can think of as the distance from the center of this planet to the center of the star. If we're talking about just one object spinning, it's more complicated than that. It has to do with the average of how far all the masses are in the object from the axis of rotation. But in general, it has to do with the size of the spin. So angular momentum is mass times radius times speed. And with this, angular momentum being conserved means that that is a quantity there. You take the planet's mass in kilograms, multiply by at any given moment its radius, meaning how far it is from the star it's going around. So in this context, it doesn't mean the radius of the planet itself. It's more the radius of the orbit at that moment, times its speed, how fast it's going in meters per second. That is some quantity. It's some big number. And that number stays the same. So notice, as it gets closer, the radius decreases. And if the entire quantity of angular momentum has to stay the same, if radius goes down, something has to go up to compensate. Mass isn't going to change, and so the only thing that can change is the speed. So as radius goes down, speed goes up, and right here, as radius is up, speed is down. So there is this trade-off between radius and speed. We talked about Kepler's second law of planetary motion in chapter 3, Johann Kepler's law, and it is that a planet sweeps out equal areas in equal times. And Isaac Newton was the one who came along in the late 1600s and showed why this is. Remember, Kepler didn't know why a planet sweeps out equal areas in equal times. He just knows that they do. And Isaac Newton showed its conservation of angular momentum, that when the planet is far away, it slows down. When it's closer, it speeds up. By the way, we have talked about in chapter 2, the Earth, that it is close to the sun in January, and it's farther from the sun in July. So when it's close to the sun, it has perihelion in January. It's actually moving a little bit faster. And when it's farther away in July, it's moving, like right here, a little bit slower. The next concepts I want to talk about are mass and weight. Now, in our everyday language, when we're talking about body weight, we often use these words interchangeably, but they are different concepts. So let's learn them. Mass is the measure of the amount of matter in an object, how much stuff is in something. So we can talk about a kilogram of water. That refers to how much water is present. We can also think of it as an object's ability to resist force. So if you push on something and it has a lot of mass, let's go back to the example of pushing a car, maybe a stalled car, and it takes a lot of force, because that car has mass, it is resisting it's resisting. But if we try to push a bus, it might be impossible unless we have many, many people doing it because the bus has more mass. So it has this greater resistance to our force. Now, I want to contrast this with weight. Weight is the force of gravity that's acting on an object. So we say that something is heavy. It doesn't necessarily mean that it's massive, although in practical everyday life, it does coincide with mass. But actually heavy, the concept of heavy refers to weight. Weight is the force that the Earth's gravity is pulling down on an object. Now, we interchange these words. We use them synonymously in everyday language because something that has more mass, also has more weight. Weight, in fact, depends on mass. But I do want you to understand these are separate concepts. And if we talk about things in outer space, it's important to distinguish between their mass and their weight because lots of places in outer space through most of the universe, there is no gravity. And so things can be weightless, and yet they still have mass. And we'll talk about that as we go on. So thought question, on the moon, and you have to understand the moon's gravity is only 1/6 as strong as Earth's gravity. So which one is true? My weight is the same, but my mass is less. My weight is less, my mass is the same. My weight is more, my mass is the same. My weight is more, my mass is less. Let's think about these. I just said that the moon's gravity is weaker. It's only 1/6 of it is on the Earth. And so the force of gravity being less, your weight would not be the same. My weight is less. Yes, that sounds right. My mass is the same. Yes, I want you to understand that mass is intrinsic to an object. It doesn't matter where you take that object in the universe, what force of gravity is acting on it. Mass has to do with how much material, how much stuff is in that object. So B looks like a good answer. Let's look at the other answers. My weight is more, my mass is the same. Well, I do agree, my mass is the same, but my weight is more, actually, because the gravity is less on the moon, that makes this statement, my weight is more, untrue. And part D, the part that says my mass is less, that's also untrue. So B is the answer. My weight is less on the moon, my mass is the same. There are other planets, other places you can go where your weight would be more and your mass would still be the same. Your mass does not depend on gravity. Something or somebody who weighs 100 pounds on Earth would weigh these numbers on various planets and moons. You don't have to memorize these numbers, but it'll come up again when we get to Chapter 7, Studying the Planets. If you were to go to the planet Mercury, and you were 100 pounds, or somebody weighing 100 pounds, that person would only weigh 37.8 pounds, because the gravity on Mercury is so much weaker than it is on Earth. On Venus, 90.7 pounds. So gravity is just a little bit weaker on Venus than it is on Earth. Mars, 37.7. Pluto is a very tiny planet, and gravity, as we'll discuss in another video, gravity relates to the size of the planet and the mass, but someone 100 pounds would only weigh less than 7 pounds on Pluto. So that person having the muscle strength to support 100 pounds in their legs could be able to jump pretty high. On Jupiter, the largest planet in the solar system, somebody 100 pounds would weigh 236.4 pounds. And so there would be a lot of stress, a lot of force pulling that person down. On the moon, as I said before, the gravity on the moon is only about 1/6 what it is on Earth. So you take 100 pounds divided by 6, you get about 16.6 pounds. And finally on Titan, which is a moon that goes around Saturn. It's the largest moon of Saturn, one of the largest moons in the solar system. The 100-pound person would weigh 11.9 pounds. Why are astronauts weightless in space? Well, it depends where you go in space, but what I'm referring to is astronauts who are in orbit around the Earth. And I want you to know that just because they're in orbit, they're off of Earth's surface, it doesn't mean there's no gravity. There is gravity in space. In fact, that's what keeps the moon in orbit around the Earth. It's what keeps the Earth in orbit around the sun. It's what keeps galaxies together. There is gravity out there. But I want you to think about something that's in orbit, and let's look at this, not to scale, this tall tower and a little diving board there, and the person just falls off. And of course, the person goes straight down, accelerating towards the center of the Earth. We call it down. But if we're zoomed out, looking at the Earth from this perspective here, the person is really falling, accelerating towards the center of the Earth. Now imagine the person runs off the diving board. The person is still going to accelerate towards the center of the Earth, but has a little bit of that lateral motion and goes in a little bit of a curve. If you throw something up in the air, not straight up, but maybe like throwing a ball high into the air and throwing it across the field, it goes in a parabola. It does this curved shape of its trajectory, and so it is constantly accelerating towards the center of the Earth. Now let's imagine this person runs so fast. By the way, the faster the person runs, the farther out the person's going to go. Like follow my red pointer here. And of course, this is embellished. This person is actually going thousands of miles, but let's just go with it. So the person running off the diving board will curve and eventually hit the ground, but just go farther. Now let's imagine using a rocket to gain enough speed, you could continually fall around Earth. That is, you'd be in orbit. So this person going fast enough, something like, I don't know the exact number, something on the order of 20,000 miles per hour, this person, just like the others who ran off the diving board, is continuously falling, accelerating towards the center of the Earth. But the Earth's surface is curving away at the same rate. And so this person is in orbit. So there's little difference between the person who jumps off a diving board and the person who is going so fast that they're in orbit. It's just that the person who is in orbit, while he is accelerating towards the ground is curving away. So he never actually intersects with the ground, never actually hits the ground. If you've ever jumped off a high height, like off a cliff or off a high diving board, for that brief moment that you are in the air, nothing is supporting you, you're just being brought down due to gravity, we say that you are in free fall. And you are feeling this thing called apparent weightlessness. It's due to a constant state of free fall. Free fall means that the only force that is acting on you is gravity. Apparent weightlessness means you're actually not weightless, because weight, remember, is the force that gravity is pulling down on you. You definitely have weight. The gravity is pulling you down towards the center of the Earth. But when we use the word apparent in science, it means that it feels like this, although it's not necessarily true. So the apparent weightlessness is you feel weightless. And it's whether you're jumping off a diving board or you are in orbit in a space station for many, many months at a time. Let's talk about moving in circles. Remember, we talked about angular momentum earlier in this video. Angular momentum describes objects that are spinning or moving in circles. There's a special force called a torque, and you can think of torque as a twisting force. It's needed to change an object's angular momentum. And so if you look at the Earth going around the sun, it is going around the sun, so it's got angular momentum there, and it's also spinning on its axis, as you can see right here with this red curve, this red arrow. So it's got the rotational angular momentum. The only way to change the angular momentum is a torque coming in, meaning some external force coming in and pushing the planet Earth over. Because there is no external force, that would be a cataclysmic thing for all life on Earth if something were to crash into us, and it would be so massive with so much momentum that it would change Earth's rotation. But aside from that happening, the Earth's North Pole is going to stay in that direction. So angular momentum is not just a matter of it spinning at the same speed or going around at the same speed. It also has to do with the direction of that axis of rotation. So it keeps pointing towards Polaris. Practically in everyday life, you think when a quarterback throws a football, there is some technique that's done. The quarterback always gives it a spin. We say he gives it the spiral. And the reason is that in giving it spin, it establishes an axis of rotation. And it's harder for it to start flopping around because it wants to keep, it has a tendency to keep that axis of rotation. So if you just throw a football without giving it a spiral, it'll start wobbling around in the air and there'll be a lot of air resistance and it won't go very far. But giving it that spin gives it a tendency to want to keep pointing in that direction, so it's going through the air with less air resistance. It's the same reason that we give a disc, a flying disc like a frisbee, a flick, we send it spinning, and so it has an axis of rotation and it has a tendency to keep that axis of rotation. Bicycles are another example. It is very hard to sit upright on a bicycle when it's not moving. No kickstand or anything, lift your feet up. Very hard to stay upright. But a bicycle that's in motion is easy to keep upright. And the reason is the wheels spinning have an angular momentum. They have a tendency to keep those wheels spinning in that particular direction that they're going, their axis of rotation pointing either to the left or to the right of the bicycle, and it's just harder to fall over. So what have we learned in this video? How do we describe motion? Speed is distance per time. When we include direction with speed, that's what's called velocity. And any change in velocity, which includes speed or direction, that's acceleration. We learned about momentum. Momentum is mass times velocity. And a force causes a change in momentum, which is also producing an acceleration. How is mass different from weight? I want you to remember that mass is a quantity of matter. We can also think of it as an object's ability to resist a force, to resist being accelerated. Weight is the force that's acting on a mass. And that is the end of the part 1 video for chapter 4. Have a great day.